Hi, good afternoon, everybody. It's an honor to be here today. And here to talk to you today about converged memory. And what I would like to get out of this is that people leave the room and start to imagine what technology like this can do to change things, change people's lives. And it sounds, a little bit grandiose, but it isn't. If anybody's familiar with the show Person of Interest, one of my favorite shows, this is all about a supercomputer, a machine somebody built that was designed, for anti-terrorism, things like that. But ultimately, what it does is it predicts when somebody's going to die or somebody's going to get murdered, and it alerts people, and they save their lives. That's the premise of the show. Now, personally, I would love to see this happen. I think that we're very comfortable getting on a plane today because we know that there are computers and systems that are keeping us safe. Nobody would get on a plane if we said, okay, we're disabling all the computers on the plane. We're only going to have one pilot, going to fly from New York to Hong Kong, and he's going to be texting his whole way there, talking to his girlfriend on the phone. Doesn't happen. Right, so computers can change our lives, but to get there, we're going to need more disruption. Things are evolving, but even in this show, they have rooms and rooms and rooms of computers that are really called the machine. And what we're here to talk about today is, can Flash be a part of that disruption that will change things? And there are some examples of how change came about to certain technologies that allowed them to evolve in certain ways that we couldn't even imagine at the time. Right? And that's the coolest part, where we look back and we say, wow, it just took a turn to the left. I didn't even see that coming. This is really, really cool. All right, so at some point in time with the television, and this is an analogy that I stole from somebody I respect very dearly, which is John Scaramuzzo from SanDisk. Somebody said at some point a huge opportunity for this is if every household has a television, right? Back in the day of black and white. Well, of course, we all know that that's not the case anymore, right? We now have 15 or 20 of them, frankly, in our homes. And I do know somebody that has 15 televisions in their home. It's very crazy, but it's possible now because it's cost effective. The form factor was completely changed. We're still a television. All it does is it shows you things, right? It shows you a television show, you see things, you play on it. But something changed, right, that completely disrupted the opportunity, the use case, and took it to another level, where today we take it for granted that you walk into somewhere and televisions are in front of you, to the left or to the right. And so that's what we're looking for in terms of Flash. I feel very strongly, and at Diablo we feel very strongly, that the full impact of this technology has not been felt yet, right? That we're at the very beginning of the ultimate disruption that is going to essentially transform computing. And today we talk about going a little faster, a little less latency, half the latency, very, very latency sensitive, and it's all true. But nobody's talking about, well, what's the fundamental pivot that's going to make people program software fundamentally completely different? How it's going to scale in a completely different manner. And I think Flash is going to be a key ingredient, and it's going to come through the form of bridging a gap between what we know as DRAM and future memory. Now, future memory, like Memristor, things like that, are actually very exciting technologies. They center around improving the density by orders of magnitude. They center around being able to be byte addressable in nanoseconds. The processor needs to be able to get access to the data, no matter where it is, instantly, so it can do work on it. Most importantly, it needs to be persistent. When you write something to it, it shouldn't forget if the power is taken away. Very important attribute that, of course, DRAM doesn't have, that many companies are trying to solve in many different ways. It has to be very cost effective. So the dollar per gigabyte, that whole paradigm has to somehow completely change for us to be, to see it as a little bit of a jelly bean, right? Just like a television. And ultimately, it has to scale, right? So whatever we do cannot just stay within one compute node, cannot stay within one computer. It has to be expandable so that it can be elastic to absorb whatever the workload of the day is, or whatever that application that is needed to be addressed can actually be serviced by that resource, right? And the resource has to actually be expandable. We think we've actually found a way to bridge that gap, and it's called converged memory, right? And I'm going to talk today about what it is, how it works a little bit, and I'm going to leave it to the imagination of everybody in the room to actually figure out, okay, well, actually, where do I think it's going to change? Where's it going to change things? So what converged memory is we take all the things from RAM that we love and all the things from flash that we love, and we kind of ignore all the things that we don't love. We ignore them because we find a way to engineer them out of the way, right? That's what we do at companies like Diablo and startups. We innovate, we dream, and then we say, okay, I'm going to not worry about this obstacle. I'm going to not worry about that obstacle. I'm going to find a way to just get around it and design it out of my way, right? And that's what converged memory is. It's actually combining all the benefits of RAM and flash together into one converged subsystem that the processor and the application see that has all the benefits that we want. It's performance, capacity, cost, endurance, and of course, most importantly, persistence. So what are the key ingredients of this? Well, last year at Flash Memory Summit, we unveiled memory channel storage, which in and of itself is very unique and, in my opinion, disruptive in a sense where we actually put something that is legitimately persistent, legitimately scalable, and very high performance on a very dedicated bus, called a memory bus, the memory subsystem. And we used it to scale the subsystem. But we still called it storage, right? We still, at that time, were accessing it through the typical means of block storage, SCSI, things like that. Still thinking like storage people, frankly, because we needed to get to market and start making revenue. Like every other company had to pay the bills. But now we can allow ourselves to start building on this platform by introducing two very, very important concepts, right? One is memory expansion, and the second is cache line persistence, which we affectionately call nano commit. All these ingredients, right, are the key to essentially bringing converged memory in a usable, very generic, compact subsystem that the application can exploit. I'm going to show you a little bit how that works. So the first thing is memory expansion. Really fancy animation here, but it's very cool. So the little white line that's scaling down the column is the CPU thread. Right? And that's what's doing work in the system. So most systems, most processors have multiple cores, multiple threads. Now what happens is when it gets to the bottom of that little DRAM column and there's nothing left for it to do, it faults. It's called a page fault. It says, hey, I wanted this information, I want to do something for you, but not here. So what happens is a storage thing happens at that point, right? The operating system gets involved and says, okay, wait, I got to go get this for you, and I got to make sure that it's available to you, but it's not going to be there for a while. Come back later. That's called swap, paging, right? Faulting. All things that are horrible, horrible to people that are centered around performance. Now, the key here on memory expansion is if you notice that the actual data is not in DRAM. Right? It's in the flash. But when the thread starts working on that data that is in the RAM, the rest of the data that's needed to complete that task is there when the thread needs it. Now, of course, there's a lot of very fancy things that are involved in making that happen, but at a very simple level, what it means is that every time the processor wants to start doing something on the data, something says, oh, I'm going to get all the associated data that's involved in this process, in this transaction, and I'm going to make it available. And the thread doesn't know. It just keeps chewing away, keeps doing work. And once it's done, it moves on, just like it was all in memory. Okay? Very powerful concept. The second, okay, so now we can imagine that if I had 12 terabytes of RAM, which is actually flash, that the application could think legitimately it had 12 terabytes of RAM. But what about saving the data, right? What about persisting it? It's very slow, right? Even memory channel storage can persist 4K of data in 3, 4, 5 microseconds, very high bandwidth, but that's like microseconds. Can't imagine an application wanting to do real-time transactions and have to wait that long. So what we do is we invent something called nano commit. And what it means is that the application writes the data into the RAM, but magically somehow that cache line or that block or whatever the resolution is, shows up in the flash. So the question is, well, how fast can it show up in the flash? Well, the cool thing is it can show up in 48 nanoseconds. Now, I don't know about everybody in the room, but to me, that's amazing. Now, I put holy whatever, and nobody edited it out, so I left it there. But I think this is cool, and I think this is amazing. What this means is that as an application is doing work, ingesting data, imagine an in-memory database that is actually ingesting new data. It's writing it into RAM. But if power is taken away from that system, all that data that it wrote is still there when it comes back up. Didn't have to do any work, didn't have to write it to I/O or create a file. It's just automatically written into the flash at a rate of 700 million random cache lines per second. Absolutely tremendous. An application today cannot actually write it that fast. We had to write one that could write it that fast. And all it does is write. It doesn't actually process anything. So in the end, these two things combined have done what previously we didn't think was possible. We can actually make flash be used like RAM, not storage. And we can actually write to RAM as fast as we can, and it will be persistent in the flash, right? And this is all done on the hardware platform that we have today, but with our innovative software, right? And this is done because we're on the memory subsystem. Our drivers are running, interfacing directly now with the application. And you notice it's the application that's writing. It's not the kernel, it's not the operating system, it's not even the BIOS, it's actually the application that now owns that space and has a pool available to it. Okay, so why does this matter? Well, if you go back to my analogy, of the television from 1925 or whatever year that was, I definitely wasn't alive back then. This is kind of that TV. Right? An in-memory database today, first of all, cannot even imagine it being deployed, on every street corner. Cannot imagine it being deployed in every room, in every desktop, at every office. It's basically a very big computer. And the data that's in memory is actually not kept permanently in memory. It's kept somewhere else, an expensive storage rate. This thing doesn't look very scalable or portable to me. It doesn't look like I can bring it everywhere and put it everywhere. But it would be more interesting if it looked like this. This I can see changing things, right? And this is real today, right? The equivalent of 60 processors and a little pizza box and literally 25 terabytes of converged, persistent, accessible memory. That can do work. That is scalable. That's cost effective. Okay? This is a platform where we can now think about, okay, I can see this changing something. I can see us doing something different than we were before. And so now we say, okay, let's talk about this compute unit and what's really different about it. Well, it's efficient in terms of the processing capability. It has this new memory capability, that we can rely on. When we write things, data doesn't go away. We read whatever we want, whenever we want, as fast as we can. Okay? And there's a lot of it. And now we can focus on just bolting on some very simple, intelligent, efficient interconnect, which is now pretty cost effective. So we take this And we can now think about scaling it into whatever size fabric we want. Right? If people are familiar with scale up or scale out, right? Scale out means you break the job up and delegate it to a whole bunch of different systems doing one little piece and bring it back together. Scale up means that that homogeneous compute node can be scaled up in capability without breaking the job up. So what's cool about this is we can scale it up before we scale it out. And hopefully never have to scale it out, frankly. Because this can do a tremendous amount of work. And what's even more interesting is it can ingest data from any number of places now, right? The more resources you can dedicate to ingesting data, the more you can process it, the more data points you can pick up. That picture I showed at the beginning that are all those images that nobody could actually put together in their minds, we can actually ingest that type of data now in a very simple platform. And we can kind of think about letting go of some of the operating system semantics that we have right now about storage, data, RAM. Doesn't exist anymore. There's objects, there's data that get ingested, they get put somewhere, and it has state. What that means is that it doesn't forget what it was doing a minute ago. And so you can take two objects, combine them, produce a third, and that's your result. It never forgets it. So this is kind of like your cell phone, but the Incredible Hulk version of your cell phone. Because that's how your cell phone works today. It bothers less and less with things like I/O and storage, and more with things like objects and state, persistence. And this is the direction we want to take things. Of course, once you bring that, the concept of real-time analysis, creating functions and capabilities on this type of platform that before were not possible, this is when things start to open up in terms of the possibilities. How is this going to change the economics? Well, did anybody ever wonder why Google gets away with using like the cheapest, bottom-of-the-barrel pizza box generic servers it can find? Well, one day I was very curious about it, and I actually looked it up. It's called warehouse computing. And what they showed through science, which was very interesting actually, they put a lot of thought into this, is that if they took a big multiprocessor machine today with lots of interconnect between the CPUs, lots of CPUs, lots of memory, and they took a job that fitted on that machine, and they put the equivalent number of pizza boxes in parallel to do the same kind of job, well, the efficiency of that big machine was orders of magnitude better than the pizza boxes. Okay, so you'd say, well, why don't they just use the big machines? Well, here's the thing, because when the problem set that they were trying to work on didn't fit in the big box, they had to put in 2 big boxes, or 4, or 8. The more big boxes they needed to fit it into, the more it started to actually look, from a performance perspective, like the pizza boxes. Except it cost 10 times more. So since Google's view is that every problem they work on doesn't fit in one machine, they created the scale-out model. Now, what's cool about what we're doing with converged memory is that we're completely changing the capabilities of that box. So science and mathematics dictate actually that the bar has to go to the left and go up, because now that capability on the right-hand side is actually almost on par with the machine on the left, if the job doesn't fit in the machine. Okay, so even from an economics perspective, if you look at the science behind it all, converged memory can actually make a huge difference in essentially the cost of the deployment of certain systems. Never mind that now it can do things that previously before were pretty much not possible. All right, so, okay, well, what are the areas that we can affect? Well, of course, in-memory computing for us, huge area. Virtualization is the foundation of scaling things out. And software defined pretty much everything, but if we had to pick one, of course, that people are familiar with, it's networking. Right, so what does that mean? It means that the generic compute node can essentially be fitted with the right kind of software, and it can affect all of these 3 specific areas. And each of these areas have companies that are working and dedicated, which are partners for Diablo, that are dedicated to making those specific areas work with Flash in a converged memory world, okay? And obviously, the key is to bring the systems out, scale them, make them available to people. And that's where partners like IBM and Supermicro come into play. And when you look at this, what you can see and you can envision is that eventually these systems that are just standard servers are going to be used eventually to replace very, very specialized pieces of hardware. Right? So what you got to do is you got to change the mindset, change the cost point. $30 per gig down to $1 per gig, right, on a NIC. Because that system can do something that the dedicated router does for much, much more money. Okay, so in the end, the coolest stuff, in my opinion, is actually yet to come. Because we're just introducing pieces that people can use as tools. Right, so in the end, I wasn't going to sit here and say, well, here are all the cool things that people can do with converged memory. Because I don't know. I don't think any one of us could have predicted, well, once we bring out something like an LED or an LCD that is going to transform the television. Just like we don't know converged memory exactly what it will transform. But I know it will transform something. And it will be cool, and we'll look back in 10 years, and we'll say that it happened today. That's it.